this is Dr. Brown. In this video, we are going to be looking at the derivative as a rate of change. You have already been introduced to the concept of the instantaneous rate of change of a function with respect to x at a point. It's just simply that the derivative at a point x naught is equal to f of x naught plus h minus f of x naught all divided by h as h goes to 0 provided the limit exists. Let's look at an example here. As everyone knows, the area of a circle is related to its diameter by this equation. I'm sure you have seen A equals pi r square. Of course, r is equal to the diameter divided by 2, so that would just simply be pi times d over 2 quantity squared, which is equal to pi over 4 times d squared. So suppose you ask the question, how fast does the area change with respect to the diameter when the diameter is 10 meters? Well, what you do is take the derivative of the area with respect to the diameter, and just using the power rule, that would be pi over 4 times the power, which is 2, times d to the power minus 1, which is equal to pi over 2 times d. And so if you wanted to see how fast the area was changing at a diameter of 10, it would be simply pi times 10 over 2, and that would be 5 square meters per meter. Now, we're going to introduce some concepts that we've already talked about a little bit. We have generally talked about S representing the position of a body at time t. And we're now formally defining the velocity v of t as the derivative of s with respect to t. And as you can see, this would be the limit of f of t plus delta t minus f of t divided by delta t as delta t goes to 0. If you're familiar with the change in t being h, this is absolutely the same as saying the limit as h approaches 0 of f of t plus h minus f of t divided by h, where h is just delta t. Here we define delta t just to show that it was a change in time past the time t. So we have instantaneous velocity, which is the derivative with respect to time of the position. Now, suppose you had a graph like this in which the position was increasing. You can look at this graph and see that ds dt, which is the slope of the tangent line, is more than 0. So if the position is increasing, it has a positive slope, so the body is moving forward. If the position is decreasing with time, then you can see that the slope of the tangent line would be negative, ds dt would be less than 0, and so the body is moving backwards. Now we're going to define what we call speed, and we call that the absolute value of the velocity. That's really how fast you're going, whether you're going forward or backwards. So if you're headed north of Swainsboro at 100 miles per hour, your velocity is 100 miles per hour. If you were headed south of Swainsboro, you might be going minus 100 miles per hour. But the speed, which is the absolute value of velocity, in both cases would be 100 miles per hour. That's how fast you're traveling. Now here is just a plot of the velocity of a body from t equals 0 to t equals 7 seconds, just showing what some of the possibilities are. As you can see here at the very beginning, the velocity is increasing between t equals 0 and t equals 1. Basically the body is speeding up. Then between t equals 1 and 2, the velocity is constant. The body is still moving forward, but its speed is constant. And then between t equals 2 t equals 3, you can see that the velocity is decreasing all the way down to 0, and so the body has been slowing down. Now between t equals 3 and t equals 4, you can see that the body is headed in the other direction. Its velocity, actually an absolute value at this particular point, is it's going the fastest that it has so far, and in fact, looking at the graph here, it's the fastest it will get. Its velocity is negative, but its speed is the largest that it has been. During this time, it's backwards, moving backwards. And then between t equals 4 and t equals 5, the negative velocity heads towards, gets smaller and smaller in absolute value, and finally the velocity goes to 0. So the body is slowing down. And then between 5 and 6 seconds, the velocity is 0, and so the body is basically standing still. And then in the last second, between 6 and 7 seconds, it speeds up again and begins to move forward. So one of the things you need to be able to do is to interpret a graph like this. Now, when you're going along in a car and you're going at a certain speed, if you see you need to speed up, you do what we call acceleration. In fact, you hit the accelerator and increase your speed. And so we define the acceleration as the derivative of the velocity with respect to time. So if a body's position is s equal f of t, then the acceleration is dv dt, which is the second derivative of the position with respect to time. And then finally, there is a term that we'll be using, which is just how fast the acceleration is changing with respect to time, and it's called the jerk, and it's just the derivative of a with respect to t, which would be the third derivative of the position with respect to time. Now, as we've already talked about, near the surface of the Earth, all bodies fall with the same constant acceleration. This came from Galileo's experiment, and you notice we've already talked about the position of an object on Earth being given by 16 t squared. That is just 1/2 times 32 times t squared, where g is the acceleration of gravity, and the 32 is 32 feet per second, and that is in English units. And you who have taken physics have seen this expressed in metric units, where s is equal to 1/2 gt squared. And on the next page we will see that expressed in metric units. Actually, before we go to the next page, I just wanted to show you the relative sizes of some planets that you know about. Obviously, here is Earth. The gravitational constant is 9.8 meters per second. And because the gravitational constant is directly proportional to the mass of the planet, you can see Venus would have a gravitational constant somewhat less than 9.8. Mars would be even less, and then you get down to Pluto, which no longer is a planet. It would be very small. And then you can look at Jupiter and Saturn, which are very small compared to Earth, and their gravitational constant would be quite a lot greater. And then the Sun would just dwarf everything. Now we're going to work a problem here, and we're going to do this one in metric units. The figure here shows the free fall of a heavy ball bearing as it's dropped from a rest position at t equals 0. And here g is 9.8, and s would be equal to 1/2 gt squared, which would be 4.9 t squared. And so the question is, how many meters does the ball fall in the first 2 seconds? And then to answer the question, what is its velocity, speed, and acceleration when t equal to 2 seconds? So just plugging in to the equation for s, we get 4.9 times 2 squared equal 19.6 meters is how far the ball falls in the first 2 seconds. Now, to calculate the velocity, we need to take the derivative of position, which is d dt of 4.9 t squared, and using the power rule, you're going to get 2 times 4.9 times t to the power minus 1, which is 9.8 t. So this gives the velocity at any time. At 2 seconds, obviously it's 2 times 9.8, or 19.6 meters per second. The speed at time t equal 2 is the absolute value of that, which is 19.6 meters per second also. Now the acceleration is the derivative of the velocity, which is the second derivative of the position. Well, we knew that the velocity was 9.8 t, so v prime is just 9.8. So the acceleration then is 9.8 meters per second squared, and we knew that. Another example, we've got an equation for the position of a heavy rock that is blown straight up with a launch velocity of 160 feet per second, which is about 109 miles per hour. This is caused by a dynamite blast, and it reaches a height of s equal 160 t minus 16 t squared after t seconds. So there are questions here. How high does a rock go? Well, there's several ways to do that, but you can calculate the velocity of the rock, which is ds dt, which would be d dt of 160 t minus 16 t squared, and taking that derivative, you get 160 minus 32 t feet per second. And the rock will continue to climb until its velocity is 0. So if we set the velocity, which is 160 minus 32t equals 0, solving for t, we get t equal 5 seconds. Now, so it climbs for 5 seconds, and to see how far it's gone, you plug this 5 into the s equation, and we get 160 times 5 minus 16 times 5 squared. Calculating this, we get that it goes up 400 feet, and then it's going to start to come back down. The next question is, what is the velocity and speed of the rock when it is 256 feet above the ground on the way up? Now, we know that it goes up to 400 feet, and so as it's climbing and reaches a 256 feet point, it wants to know what the velocity and speed of the rock is when it's 256 feet. So we have to set the position equal to 256 feet and solve for t to find out what are the times when the rock is exactly 256 feet high. So solving this equation for t, we get a quadratic equation. We take 256 over to the other side, and actually uh, we're taking these terms over to the other side and creating a quadratic equation with 16t squared is positive on the other side. So we get an equation 16t squared minus 160t plus 256 equals 0. You immediately see you can factor 16 out and get a simpler quadratic equation, t squared minus 10t plus 16. Set it equal to 0, and this particular one can be factored into t minus 2 times t minus 8. Always check your factors, and you'll find, in this case, that at t equal 2 seconds and t equal 8 seconds, that these are the points in time when the rock is exactly 256 feet above the ground. So the rock's velocity at these times can be determined by the velocity equation. Remember, the velocity was equal to 160 minus 32t. So plugging 2 in, we get 160 minus 64, or plus 96 feet per second. So its velocity is positive on the way up. Calculating this at t equal 8, when it's on the way down, we get 160 minus 32 times 8 equal minus 96 feet per second. Notice its actual speed is exactly the same at t equal 2 seconds and at t equal 8 seconds. And then the next question is, what is the acceleration of the rock at any time t during its flight? Well, the acceleration is dv dt. And recall that the velocity was 160 minus 32t. Taking that derivative, we get minus 32 feet per second. And that's written as minus 32 feet per second squared. So the acceleration of gravity, as you know, is always downward. It's always trying to bring anything above the surface of the earth down towards Earth, unless it's acted upon by another force, like a rocket taking off, or you're throwing a ball up. Now the last question is, when does a rock hit the ground? And of course a rock hits the ground at the positive time t, for which s is equal to 0. So you recall that s was given by 160t minus 16t squared. Setting that equal to 0, you obviously can factor 16t out, and you get 16t times 10 minus t equals 0. The solution to this is t equals 0. Obviously that's at the very beginning when the ball, when the rock is blasted up. The other time is t equal 10 when it hits the ground. So the ball hits or rock hits the ground 10 seconds after the blast occurs. So now we see here on this slide, first of all, the position versus time of the rock. We see it going up to a maximum position of 400 feet. And you remember at t equal 2 and then t equal 8, it was at 256 feet. We've also plotted the velocity of this rock, which was 160 minus 32t, which is a straight line. And you can see that the velocity is positive for the first 5 seconds when the rock is on its way up, and the velocity becomes negative on the next 5 seconds as it comes back down to the ground.